There is a moment just before sleep when the mind lets go of certainty and drifts into older truths. In that quiet space between waking and dreams, perhaps we remember things that logic has forgotten. Perhaps we remember a sky the colour of rust, stretching endlessly above plains where no blue ocean ever reflected sunlight. Perhaps we remember home. Could it be that our story began not here, beneath these familiar stars, but somewhere else entirely? Somewhere where the horizon burned amber and the wind carried whispers of a world slowly forgetting how to breathe. This is not a question science asks lightly, yet it lingers in the spaces between what we know and what we feel when we look up at that distant red dot, hanging like a memory in our night sky. We call ourselves children of Earth, born from blue water and green leaves, shaped by gravity that feels as natural as our own heartbeat. But what if this belonging is newer than we think? What if the pull we feel toward Mars, that inexplicable longing that drives us to spend fortunes and lifetimes dreaming of red soil beneath our feet, is not curiosity at all, but something deeper, quieter, more ancient than our recorded history can contain? The possibility settles like dust in the mind. Mars, that cold and distant world, spinning through space with the patience of something that has learned to wait. Mars, whose very name carries the weight of war and endings, yet whose surface holds secrets written in a language we are only beginning to remember how to read. What if Mars is not our destination, but our beginning? What if every human who has ever looked up at the night sky and felt that inexplicable pull toward the Red Wanderer is feeling not wonder, but homesickness? Consider the strangeness of our obsession. Among all the worlds we might explore, among all the distant suns and impossible planets that dance beyond our reach, we return again and again to Mars. We send our mechanical children there, our rovers and landers, our eyes and hands reaching across the void, with a desperation that feels less like exploration and more like reaching toward something we have lost. We map its canyons as if we are trying to remember the way home. We search its soil as if we are looking for something we buried there long ago. The evidence, if we call it that, lives not in telescopes or laboratories, but in the quiet consistency of human yearning. Generation after generation, we have imagined ourselves walking on Martian ground with the familiarity of returning travellers. We have dreamed of breathing its thin air as if our lungs remember a different kind of sky. We have spoken of terraforming Mars as if we are not changing it but restoring it, bringing it back to something it once was, something we once knew. Science, careful and methodical, tells us that Earth is our cradle, that every bone in our body and every breath in our lungs bears the signature of this blue world's particular chemistry. Yet science also tells us that worlds are not isolated islands, but part of an intricate dance of exchange, where meteorites carry fragments of one planet to another across millions of years, where life itself might travel between worlds like seeds on cosmic winds. The timeline stretches behind us into darkness, billions of years of planetary evolution that we glimpse only in fragments. Earth's early history is written in rocks that have been recycled, reformed, erased and rewritten by the patient work of geology. But Mars, cold and still, might remember things that Earth has forgotten. Mars might hold the memory of what came before, preserved in its silence like words written in a language we no longer speak. What if the reason we have never found clear evidence of life's beginning on Earth is because life did not begin here? Others shattered mountains and boiled away atmospheres, creating temporary lakes of molten rock that cooled into glass, preserving the moment of collision like insects trapped in amber. But perhaps the most eloquent speakers in this planetary archive are the stones that seem ordinary, the rounded pebbles that lie scattered across ancient riverbeds, polished smooth by water that flowed when Earth was still a violent young world, when life on our planet consisted of nothing more complex than chemical conversations in warm tidal pools. These pebbles speak of patience, of water that had time to work its gentle magic, tumbling stones for thousands of years until their edges wore away, until they became perfect spheres that catch the light like drops of frozen time. The silence between the stories is as meaningful as the stories themselves. Mars speaks in whispers and pauses, in the spaces between dust grains where ancient chemistry might still linger. Modern instruments can detect molecules that formed billions of years ago, organic compounds that speak of processes we are only beginning to understand. Some of these molecules could form without life, through the patient work of geology and chemistry. Others, more complex and fragile, seem to require something more intentional, something that organized carbon and hydrogen and oxygen into patterns that chemistry alone cannot easily explain. Water carved this language most eloquently of all. Everywhere our mechanical explorers look, they find the signatures of ancient flow. Channels carved by flash floods, deltas where rivers once emptied into lakes, mineral deposits that form only where water pooled and evaporated, leaving behind the dissolved memories of vanished seas. The water spoke in many dialects, sometimes rushing and urgent, carving deep gorges in a matter of days, sometimes patient and persistent, laying down sediment grain by grain across geological ages. Some of this water still speaks, though in whispers, frozen into polar caps that grow and shrink with the Martian seasons, locked into permafrost that lies just beneath the surface, hidden in underground aquifers that might still flow in the planet's deep places. This water remembers the taste of a different Mars, a Mars where clouds gathered and rain fell, where rivers ran year-round and lakes reflected not just sunlight but perhaps other lights as well, the phosphorescent glow of life beginning to experiment with existence. The wind, too, has written its stories across the Martian surface, creating sculptures that would take human artists lifetimes to conceive. Sand dunes migrate across the landscape like slow-motion waves, their shapes recording the prevailing winds of seasons and centuries. Dust devils dance across the plains, visible from orbit as dark tracks that spiral across the surface, temporary calligraphy written by the marriage of heat and motion. Even the chemistry of the Martian atmosphere speaks, though in molecules so sparse they barely constitute a whisper. The thin air holds traces of methane that appear and disappear with mysterious regularity, noble gases that tell stories of atmospheric escape, isotope ratios that speak of a planet slowly forgetting how to hold on to its breath. Each measurement is a word in a conversation that has been continuing for billions of years, a conversation between a planet and the space that surrounds it, between matter and energy, between memory and entropy. This is the library that awaits us, written in a language we are learning to read one grain at a time. Every sample our rovers collect, every photograph they transmit across the vast darkness, every chemical analysis they perform is another lesson in Martian literacy. We are like archaeologists excavating not just ruins but an entire vocabulary, learning to translate the subtle dialectives of stone and dust and wind-carved cliff faces. And yet, as we learn to read this ancient language, we cannot escape the feeling that it is somehow familiar, that these stories of water and wind and slow geological transformation echo something we already know. Perhaps this is simply the universal nature of planetary evolution, the way all worlds speak similar languages of erosion and accretion, of heating and cooling, of atmospheres gained and lost. Or perhaps it is something more specific, more personal, the recognition that comes when we encounter words we once spoke ourselves in a voice we thought we had forgotten. Once, when the solar system was young and still learning its rhythms, Mars may have worn oceans like jewelry, vast bodies of water that caught and held the light of a sun not so different from the one that warms us now. If you could have stood on the shore of such a sea, feeling alien sand between your toes and breathing air thick enough to taste, what would you have seen reflected in those ancient waves? The evidence lies scattered across the Martian surface like memories of a dream half remembered upon waking. Orbital photographs reveal the unmistakable signatures of ancient coastlines, curved and gentle where waves once lapped against shores that are now nothing but dust and stone. These phantom beaches stretch for thousands of kilometers, marking the edges of seas that may have been deeper than Earth's Mediterranean, wider than any lake our world has ever known. The northern lowlands of Mars spread out like the floor of a vanished ocean, smooth and flat, in the way that only deep water can make land smooth. Here and there, islands of higher ground rise from these ancient depths like mountain peaks remembered in topographic maps. If water once filled these basins, it would have created a world transformed, a Mars where the sound of waves competed with the whisper of wind, where storms brought rain instead of dust, where life might have found its first tentative foothold in the chemistry of the mathematics of such an ocean stagger the imagination. Scientists calculate that Mars may once have held enough water to cover its entire surface to a depth of several hundred meters, or to fill ocean basins deeper than any on Earth. This water did not appear suddenly. It accumulated over millions of years as comets and asteroids delivered ice from the outer solar system, as volcanic outgassing released water vapor trapped in the planet's crust, as the slow alchemy of planetary formation turned raw materials into the complex chemistry of a living world. But water alone does not make an ocean. For liquid cease to exist on Mars, the planet needed an atmosphere thick enough to maintain stable temperatures, dense enough to prevent water from simply boiling away into space. The evidence suggests that early Mars may have possessed just such an atmosphere, perhaps dominated by carbon dioxide, that created a greenhouse effect, trapping solar heat and maintaining temperatures where water could exist as a liquid rather than ice or vapor. This ancient Martian climate may have been nothing like Earth's gentle seasons. The planet's orbit carries it much farther from the Sun, and even with a thick atmosphere, Martian oceans would have been cold, perhaps frigid by Earth standards. Yet cold oceans can still teem with life, as Earth's polar seas demonstrate. Cold water holds more dissolved gases, more nutrients, more of the complex chemistry that life requires to begin its patient work of self-organization. Imagine those first Martian tides, pulled by two small moons that painted strange shadows across the water. The larger moon, Phobos, would have raced across the sky 3 times in a single day, creating tidal cycles unlike anything we know on Earth. These rapid tides might have created vast tidal zones, areas of alternating wet and dry, that could have served as laboratories for the chemistry of early life, places where organic molecules had time to concentrate and experiment with new forms of complexity. The minerals dissolved in these ancient seas would have told their own stories. As water flowed from highlands to lowlands, it would have carried with it the chemical heritage of Martian rocks, creating brines rich in sulfates and chlorides, in iron and magnesium, in all the trace elements that Earth life has learned to use in its metabolic choreography. Some of these minerals, like the perchlorates that modern Mars rovers detect in Martian soil, would have been toxic to Earth life as we know it. But life has always been inventive, always willing to work with whatever chemistry it finds available. The seasonal cycles of such a world would have painted the planet in colours we can barely imagine. If Mars had an atmosphere thick enough to support liquid water, it might also have supported weather systems vast and strange. Dust storms might have given way to rainstorms, blizzards of snow and ice, perhaps even the gentle precipitation of organic compounds that fell like manna from photochemical reactions in the upper atmosphere. As the eons passed, this oceanic Mars would have faced the same patient erosion that claims all planetary atmospheres. Solar wind, that constant stream of particles from the Sun, would have slowly stripped away the Martian air molecule by molecule by molecule. Without the protection of a strong magnetic field, Mars could not hold on to its atmosphere indefinitely. Gradually, inexorably, the seas would have begun to shrink. The death of a planetary ocean is not a sudden catastrophe, but a slow fade, a process that might take millions of years to complete. As the atmosphere thinned, the seas would have grown saltier, more concentrated, more alkaline. Some areas would have dried completely, leaving behind vast salt flats that still mark the Martian surface like scars. Other regions might have persisted longer, becoming increasingly exotic as they concentrated minerals and chemicals into brines unlike anything in our terrestrial experience. Some of this water may have retreated underground, seeping into the porous rocks and frozen soils that still hold Martian ice today. Recent discoveries suggest that liquid water may still exist in underground aquifers, in seasonal flows that darken Martian cliff faces, in the deep chemistry of rocks that have never completely forgotten the taste of ancient seas. But if life swam in those vanished oceans, if Martian seas once hosted their own versions of the patient chemistry that eventually gave rise to consciousness, what happened to that living heritage? Life is persistent, inventive, capable of surviving in environments that seem impossible to our terrestrial perspective. Earth life has learned to thrive in boiling springs, in crushing deep ocean pressures, in radiation fields that would sterilize most complex chemistry. Martian life, if it ever existed, might have developed even more exotic survival strategies. Perhaps some remnant of that oceanic heritage still rests in the deep places of Mars, in caves and aquifers, where the patient work of biology continues in forms we have not yet learned to recognize. Perhaps fragments of that ancient story traveled across the gulf between worlds, carried by meteorites that preserve not just minerals but genetic memory, organic molecules that remember the taste of alien seas. The possibility lingers like starlight reflected in water, beautiful and distant and impossible to grasp directly. But a truly advanced civilization might create markers even more durable than our accidental signatures. Structures built from engineered materials, designed to last, might persist in the Martian subsurface like artifacts waiting for archaeologists who have not yet learned where to dig. Underground installations, built to survive the loss of atmosphere and the cooling of a planet, might still exist in the deep places of Mars, preserved by the same cold and dryness that has kept Martian meteorites intact for billions of years. The search for Martian fossils faces challenges that Earth paleontology never encounters. Mars has no easy access to its sedimentary layers, no convenient road cuts or eroding cliffsides where ancient strata lie exposed and accessible. The planet's surface has been sandblasted by eons of dust storms, potentially destroying any fossils that might once have been preserved in surface rocks. The most promising fossil sites are likely buried deep beneath protective layers of later sediment, accessible only to drilling equipment we have not yet deployed. Even if we find organic compounds in Martian rocks, and we have already begun to detect them, the question of their origin remains tantalizingly open. Organic chemistry can arise through purely geological processes, through the patient work of water and minerals and geological heat. But it can also arise through biological processes, through the complex dance of self-organizing chemistry that we call life. Distinguishing between these possibilities requires not just the detection of organic compounds, but analysis of their structure, their isotope ratios, their arrangement into patterns that speak of intention rather than accident. The most intriguing fossils might not be biological at all, but geological structures in rock that speak of environmental conditions unlike any Mars has known in recorded history. Fossil raindrop impressions preserved in ancient mudstones, fossil beach sand patterns that speak of tides and waves, fossil soil horizons that formed under thick atmospheres and gentle rains. These geological fossils would tell stories of a Mars transformed, a Mars that once wore weather like a comfortable coat, where the patient work of erosion and deposition followed rhythms we can barely imagine. Recent discoveries have already begun to reveal tantalizing hints of Martian preservation processes. Some Martian rocks contain mineral patterns that could only form in the presence of liquid water, while others preserve chemical signatures of ancient thermal springs, environments where Earth life thrives and where fossilization occurs under unique conditions. These thermal environments might have served as refuges where life could persist even as Mars's climate cooled, oases of warmth and chemistry in an increasingly hostile world. The rovers we have sent to Mars are our first tentative attempts at Martian paleontology, equipped with instruments that can analyze rocks and soils at the molecular level, searching for the chemical signatures that might betray the presence of ancient life. But they are limited to surface materials, to rocks that have been weathered and altered by millions of years of exposure to the Martian environment. The true fossil record of Mars, if it exists, likely lies deeper in sedimentary layers that have been protected from surface weathering in underground environments where the chemistry of preservation has been allowed to work undisturbed. Accessing these deeper layers will require not just more sophisticated rovers, but drilling capabilities, sample return missions, perhaps eventually human paleontologists working with hammers and brushes in the Martian field. And if we find them, if we uncover fossils that speak unmistakably of Martian life, or traces of structures that speak of Martian intelligence, what then? The discovery would transform our understanding not just of Mars, but of ourselves, of the relationship between worlds, of the possibility that consciousness is not unique to Earth, but part of a larger conversation that spans planets and geological ages. Perhaps the most profound fossils would be those that seem familiar, that speak of evolutionary patterns we recognize, of chemistry that follows rules we understand. Such discoveries might suggest not just that life can arise independently on different worlds, but that life follows universal patterns, that the universe itself is predisposed toward complexity, toward consciousness, toward the patient work of self-awareness that allows matter to contemplate itself across the depths of space and time. The universe practices a gentle form of correspondence, sending letters between worlds in envelopes of stone and metal that travel for millions of years before reaching their destinations. These cosmic messengers, meteorites torn from planetary surfaces by ancient impacts, carry within them more than just mineral samples. They carry the possibility of memory, of genetic heritage, of conversations between worlds written in languages older than consciousness itself. 4. Every year, Earth receives thousands of these stone letters, most no larger than grains of rice, burning bright trails across our night sky before settling silently into fields and forests and ocean depths. Most come from asteroids, fragments of the solar system's violent youth when planets were still accreting from cosmic dust and debris. But some carry more intimate messages, samples chipped from the surfaces of Mars and the Moon by impacts so powerful they could launch rocks into interplanetary space, where they drift for eons before gravity guides them to new homes. The Martian meteorites that have reached Earth tell stories of their homeworld that no telescope could reveal, stories written in crystal structure and isotope ratios, in mineral compositions that match the chemical signatures our rovers have detected on the Martian surface. But these stones have travelled farther than any human explorer, have seen more of the solar system than our most ambitious spacecraft, drifting through the cold emptiness between worlds while carrying samples of Martian geology in their crystalline memories. But could these interplanetary messengers carry more than just geological information? Could they preserve, in their microscopic structures, fragments of biological heritage that speak of life's ability to survive journeys that span not just space but time? The idea seems fantastical until we consider life's remarkable persistence, its ability to survive in environments that seem impossible to our terrestrial perspective. On Earth, we have discovered life forms that challenge every assumption about biology's limitations. Bacteria that thrive in the radioactive cores of nuclear reactors, archaea that metabolize sulfur in boiling springs, tardigrades that can survive the vacuum of space, the crushing pressures of deep ocean trenches, temperatures that approach absolute zero. Life, it seems, is not fragile, but inventive, not limited by the conditions that seem comfortable to us, but capable of adaptation that borders on the miraculous. Some of these terrestrial extremophiles might survive the journey from Mars to Earth, locked inside meteorites that protect them from the worst radiation and temperature extremes of interplanetary space. The interior of a large meteorite remains relatively stable during its journey, shielded from cosmic radiation by the surrounding rock, insulated against the extreme temperature variations of space. For bacteria or other microorganisms already adapted to extreme conditions, such a journey might be challenging, but not impossible. The timeline of interplanetary transfer adds another layer to this possibility. While most Mars-to-Earth journeys take hundreds of thousands or millions of years, some meteorites complete the trip in much shorter periods, thousands or tens of thousands of years, timescales within which hardy microorganisms might maintain some form of dormancy or cryptobiosis, waiting for conditions favorable to awakening. Recent discoveries have made this scenario seem less speculative and more scientifically plausible. We have found organic compounds in Martian meteorites, complex carbon-based molecules that could form through purely geological processes, but might also represent the chemical signatures of ancient biological activity. Some of these compounds show isotope ratios that differ from typical geological processes, ratios that on Earth often indicate biological rather than purely chemical origins. More intriguingly, some Martian meteorites contain structures that resemble fossilized bacteria, microscopic forms that look remarkably similar to Earth microorganisms, but with subtle differences that suggest they might represent a distinct evolutionary heritage. The debate over these structures continues, with scientists divided between those who see evidence of ancient Martian life and those who interpret the same structures as purely mineral formations that coincidentally resemble biological forms. But the implications extend beyond individual meteorites to the larger process of planetary exchange that has been occurring throughout the solar system's history. If life can survive interplanetary transfer, then the solar system becomes not a collection of isolated worlds, but a connected biological system, where life arising on one planet might eventually seed life on others, creating a cosmic ecology that spans worlds and geological ages. This process, called panspermia, suggests that life might not need to arise independently on each world, but could spread from planet to planet through the patient work of cosmic bombardment and gravitational dynamics. In this scenario, the question is not whether life arose on Mars or Earth first, but whether the distinction matters at all. Life might be a solar system phenomenon, a cosmic experiment that uses planets as laboratories, transferring its results from world to world through stone messengers that carry biological heritage across the emptiness between planets. The early solar system was particularly conducive to such transfers. When the planets were young and still experiencing heavy bombardment, impacts were more frequent and more powerful, capable of launching larger quantities of material into interplanetary space. The orbits of Mars and Earth were slightly different then, creating transfer opportunities that might have been more frequent than they are today. During this period, both Earth and Mars were more hospitable to life than they are now. Earth's atmosphere was different, its surface largely covered by a global ocean that provided stable conditions for early biology. Mars still possessed a thicker atmosphere and surface water, creating environmental conditions that might have supported not just the origin of life, but its development into forms complex enough to survive interplanetary transfer. If transfer occurred during this ancient period, it might help explain some of the puzzles in Earth's early biological history. The rapid appearance of complex cellular structures in Earth's geological record, the sophisticated biochemistry of even the earliest known life forms, the universal genetic code that all Earth life shares. These features might make more sense if life on Earth had a head start. If it began not from simple chemical precursors, but from more complex biological heritage that arrived pre-packaged in Martian meteorites. The possibility works in both directions. If life arose first on Earth, it might have seeded Mars through the same process of impact ejection and interplanetary transfer. The massive canyons and impact craters that dot the Martian landscape are billions of years old, protected from erosion by the thin atmosphere and lack of liquid water that would have long ago erased similar features on our more active world. But this preservation comes at a cost. Mars's geological stillness, which allows it to remember its ancient surface features, also means that its deep interior has cooled and solidified, ending the magnetic dynamo that once protected its atmosphere from solar wind erosion. The same processes that preserved Mars's ancient memories also doomed it to lose its atmosphere, its water, its ability to maintain the complex chemistry that might have supported life. Earth's more active geology erases individual memories, but maintains the conditions necessary for continued evolution, for the emergence of new forms of complexity that can themselves become agents of memory and consciousness. Our planet's forgetfulness at the geological level has enabled its remembering at the biological level, creating conditions where information can be preserved, not just in rock and ice, but in the genetic codes of living organisms, in the neural networks of evolving brains, in the cultural memories of species that have learned to remember themselves. The isotope ratios preserved in ancient rocks speak to the most fundamental forms of planetary memory, recording the nuclear processes that occurred during the solar system's formation and the subsequent evolution of planetary atmospheres. Each isotope is a timestamp, a chemical signature that records specific conditions at specific times in planetary history. The ratios of noble gases in Martian and terrestrial atmospheres tell stories of atmospheric escape, of solar wind stripping, of the different evolutionary paths that led Mars and Earth to their current states. These isotope memories reveal that Mars once possessed an atmosphere much thicker than its current thin veil of carbon dioxide, an atmosphere that might have created greenhouse conditions warm enough to support liquid water on the surface. The gradual escape of this atmosphere, recorded in the changing ratios of light to heavy isotopes, tells the story of a planet slowly forgetting how to breathe, losing its ability to maintain the complex chemistry that connects atmosphere, hydrosphere, and geosphere into a unified planetary system. But even as entropy works to erase planetary memories, it also creates new forms of information, new patterns that emerge from the interaction between order and chaos. The dust storms that rage across Mars for months at a time are expressions of entropy, chaotic systems that dissipate energy and increase disorder. Yet these same storms create their own patterns, their own forms of organization, sculpting the Martian landscape into forms of beauty that emerge from purely physical processes. The seasonal changes on Mars, subtle but detectable from orbit, reveal another form of planetary memory that operates on shorter timescales. As carbon dioxide freezes out of the atmosphere at the poles during Martian winter, the planet's atmospheric pressure drops globally, creating a rhythm of atmospheric breathing that has persisted for millions of years. This seasonal cycle is Mars's way of remembering its relationship with the Sun, its elliptical orbit, its axial tilt, maintaining a pattern of change that connects the planet to larger cosmic rhythms. Water on Mars exists now primarily as ice, locked in polar caps and underground permafrost, preserved in a state of suspended animation that could last for geological ages. This ice is itself a form of memory, holding within its crystal structure the chemical composition of ancient Martian atmospheres, preserving isotope ratios and dissolved gases that speak of different climatic conditions. Should Mars ever regain a thicker atmosphere, this water could return to liquid form, carrying with it the dissolved memories of earlier epochs. The organic compounds detected in Martian soils and rocks represent another form of planetary memory, carbon-based molecules that might preserve information about ancient biological or pre-biological chemistry. These compounds exist at the boundary between geology and biology, between entropy and information, speaking of chemical processes that might have occurred when Mars was more hospitable to complex chemistry. Whether these compounds formed through purely geological processes or represent traces of ancient life, they constitute a form of molecular memory that has survived billions of years of planetary evolution. Even the loss of memory can become a form of memory itself. The absence of certain isotopes in the Martian atmosphere tells the story of atmospheric escape, while the presence of others records the processes by which Mars has been slowly losing its ability to maintain liquid water on its surface. The planet's magnetic field, now largely absent, is remembered in the magnetic minerals locked in ancient rocks, preserving the signature of a time when Mars could protect its atmosphere from solar wind erosion. This interplay between memory and forgetting, between preservation and entropy, suggests that planets are not passive objects, but active participants in the universe's tendency toward complexity. They serve as libraries and laboratories, preserving information about cosmic processes while creating conditions where new forms of information can emerge. The geological and atmospheric memories preserved by planets become the foundation for biological memories, for the genetic information that allows life to evolve and adapt and eventually to contemplate its own origins. Perhaps consciousness itself emerged as the universe's answer to entropy, a way for matter to organize itself into patterns capable of preserving and transmitting information across time and space. In this view, the planetary memories preserved in rock and ice and atmosphere are not separate from biological memory, but part of a continuum, a cosmic conversation between different forms of information processing that connects the chemistry of stars to the thoughts of minds contemplating their but place in the universe. There is a particular quality to ruins that speaks louder than any monument ever built to last, a silence that carries more weight than the loudest proclamation of power or achievement. On Earth, we have learned to read these silences, to find in broken columns and buried cities the stories of peoples who believed their works would endure forever, who built in stone and bronze and dreams of permanence, only to discover that time is more patient than any human ambition. But what of civilizations that might have arisen under different skies, on worlds where the very nature of time and preservation follows different rules? What of Mars, where the thin atmosphere and geological stillness might preserve some traces of intelligence while erasing others, where the patient work of sandblasting winds might leave signatures of consciousness written in forms we have not yet learned to recognize? The challenge of detecting ancient civilizations grows exponentially with time. On Earth, structures that are mere thousands of years old require careful archaeological work to uncover and interpret. Cities that flourished during the height of human civilization have been reduced to foundation stones and pottery shards, their stories readable only to specialists who have learned the subtle language of ruins. Extending this timeline to millions or billions of years transforms the problem from difficult to seemingly impossible, yet not necessarily hopeless. Consider the forms that evidence of intelligence might take on a world like ancient Mars, where different environmental conditions would have favored different approaches to construction and preservation. A civilization that evolved in an environment with thin atmosphere and extreme temperature variations might have built primarily underground, creating networks of tunnels and chambers that could survive surface bombardment and atmospheric loss. Such structures, carved into bedrock and sealed against the elements, might persist far longer than any surface construction. The geological stability of Mars could work both for and against the preservation of artificial structures. The lack of active plate tectonics means that features can persist for billions of years without being recycled into the planet's interior, but it also means that impact cratering and wind erosion have had eons to work their destructive magic on anything exposed to the surface. The sweet spot for preservation might lie in the intermediate depths, below the reach of surface erosion, but above the level where geological pressure could deform or destroy artificial cavities. If Martian civilization existed, it might have left signatures we would not immediately recognize as artificial. A truly advanced society might have learned to work with geological processes rather than against them, creating structures that appear natural to casual observation, but reveal their artificial nature only under careful analysis. Tunnels that follow two perfect mathematical curves, chambers with proportions that speak of intention rather than accident, mineral compositions that occur nowhere else in nature. The absence of obvious ruins might itself be evidence of sophistication rather than absence. Earth civilizations have typically announced their presence through massive construction projects, pyramids and temples and cities that proclaim human ambition across the landscape. But a civilization that understood the deep time scales of planetary evolution might have chosen subtlety over grandeur, creating markers designed to survive not centuries or millennia, but geological ages. Such markers might be written in the language of geology itself, isotope ratios deliberately altered from natural patterns, mineral formations that could only result from industrial processes, layers of sediment that contain trace elements in proportions that speak of large-scale technological activity. A civilization capable of nuclear technology might have left radioactive signatures locked into rock formations, artificial isotopes that would remain detectable for millions of years after their creation. The very absence of certain features on Mars might constitute evidence of past intelligence. The planet's surface shows signs of massive water flow and erosion, yet lacks the river deltas and sedimentary formations that such flows should have created. Could some of these missing geological features have been deliberately modified or removed? Could the unusual smoothness of certain Martian plains result not from natural processes but from large-scale engineering projects designed to create infrastructure we cannot yet recognize? Even more intriguingly, Martian civilization might have left markers written in the planet's orbital characteristics or rotational dynamics. Advanced societies capable of planetary engineering might have altered Mars's axial tilt, orbital period, or rotational rate in ways that would persist long after their surface traces had been erased. Such modifications would be detectable to civilizations capable of precise astronomical measurement, but might appear as natural phenomena to less advanced observers. The search for technological artifacts faces the challenge of deep time erosion. Metals corrode, plastics decompose, even the most durable materials eventually succumb to radiation damage and chemical weathering. But some technological signatures might persist in forms we are only beginning to consider. Artificial isotopes created by nuclear processes, engineered bacteria or viruses that retain traces of their artificial origins in their genetic codes, quantum scale modifications to matter that remain detectable across geological time. Perhaps the most durable monuments a civilization could create would be written not in matter, but in information, in patterns that could survive the destruction of their physical substrate. A sufficiently advanced society might have encoded messages in the genetic structures of extremophile organisms, creating biological archives that could survive planetary catastrophe. They might have carved information into the quantum structure of certain materials, creating messages readable only to civilizations that had developed appropriate technology. The silence of Mars might itself be a form of communication, a message written in absence rather than presence. A civilization that understood the inevitability of planetary climate change might have chosen to leave deliberately, to seek homes among the stars rather than face slow extinction on a cooling world. Their absence might be not tragedy but wisdom, not failure but success in recognizing and responding to cosmic cycles beyond their control. Current searches for Martian life focus on microscopic organisms, on the chemical signatures of simple biology, but future explorations might need to develop new methodologies for detecting the signatures of intelligence across geological time. This would require not just better instruments, but new ways of thinking about what constitutes evidence of consciousness. What forms of pattern and organization might persist when all obvious artifacts have long since turned to dust? The implications of discovering such evidence would transform our understanding not just of Mars, but of intelligence itself, of consciousness as a cosmic phenomenon rather than a terrestrial accident. If intelligence arose on Mars during its habitable period, if consciousness once contemplated Martian sunsets and wondered about the nature of existence under alien skies, then intelligence becomes not a rare exception, but a natural expression of cosmic evolution. As fundamental to the universe as gravity or electromagnetism, and perhaps that is what we are really searching for when we send our rovers across the Martian landscape, when we analyze soil samples and photograph rock formations with such methodical dedication. We are not just looking for microbes or organic compounds, but for evidence of minds like our own, for consciousness that once asked the same questions we ask, for intelligence that once looked up at the night sky and wondered what other minds might be looking back. The silence of Mars is profound, but silence can speak in many languages. Perhaps we have not yet learned to hear what it is saying, to recognize in the patient dignity of ruins the monuments that matter most, the evidence of minds that once dared to think and dream and wonder under a red sky, that remembers everything and reveals its secrets only to those who know how to. Listen to the deeper music of time and stone and possibility. Time, in its cosmic patience, moves not in straight lines, but in cycles, great wheels of change that turn so slowly that civilizations rise and fall between the tick and tock of geological chronometry. As we peer through telescopes at the rust-coloured surface of Mars, seeing in its barren plains and empty riverbeds the ghost of a world that once knew water and weather, we might be looking not into the past, but into a mirror, seeing reflected there not where we came from, but where we are going. Earth today pulses with life, its blue oceans teeming with creatures that have never known any sky but this one, its green continents carpeted with forests that breathe our atmosphere into existence with every photosynthetic breath. Our world seems permanent, eternal, as fixed and reliable as gravity itself. Its core cooled and its magnetic field weakened, its atmosphere slowly bled away into space. Its water followed the atmosphere into the cosmic void, and what had once been a blue world under rust-coloured skies became the red desert we observe today. Earth is larger than Mars, with a more massive core that generates a stronger magnetic field and takes longer to cool. Our planet orbits closer to the Sun, receiving more energy to drive the atmospheric and oceanic circulation that distributes heat and maintains climate stability. These advantages have given Earth a longer period of habitability, but they do not make our world immune to the same physical processes that transformed Mars. The atmospheric escape that claimed Mars's air continues on Earth at a much slower rate, imperceptible on human timescales but significant over geological time. Earth loses hydrogen to space continuously, a process that will eventually limit our planet's ability to maintain liquid water. The exact timeline remains uncertain, but the process is as inevitable as the Sun's gradual brightening, as inexorable as the cooling of planetary cores and the weakening of magnetic fields. Yet perhaps the most important lesson Mars offers Earth is not about inevitable endings, but about the preciousness of beginnings, about how rare and valuable the conditions for complex life really are. If Mars was once a living world, then our solar system has already witnessed the death of one biosphere, the slow fade of an entire planet's worth of evolution and complexity and consciousness. This history transforms every living thing on Earth into a refugee from cosmic processes larger than any individual world, a survivor of forces that have already claimed at least one planet's worth of life and dreams and possibilities. The mirror Mars holds up to Earth reflects not just our possible future, but our current responsibility, our role as perhaps the only consciousness in our solar system capable of understanding these cosmic cycles and potentially responding to them. If we are indeed the inheritors of Martian memory, if life on Earth carries within it the genetic heritage of a vanished Martian biosphere, then we bear the responsibility not just for our own survival, but for preserving the accumulated wisdom of 2 worlds' worth of evolution. This perspective transforms space exploration from luxury to necessity, from curiosity to obligation. If Earth follows Mars's path toward uninhabitability, if our blue world eventually becomes another red desert circling a brightening star, then our survival as a species depends on our ability to carry life beyond the cradle of individual worlds. We must learn to live among the stars, not because space calls to our sense of adventure, but because physics demands it, because the same laws that created habitable worlds also ensure that no world remains habitable forever. Mars, in this view, is not just our possible past, but our necessary future. The world we must learn to inhabit, not because we choose exile, but because exile may choose us. The red planet that calls to us across the darkness may be calling us home not to the world we came from, but to the world we must learn to make our own, teaching us the skills we need to survive when Earth itself becomes a memory written in stone and starlight. And perhaps this is why Mars haunts our imagination with such persistence, why we dream of red soil and rust-coloured horizons with the intensity of homesickness. Perhaps we recognise in Mars not alien landscape, but familiar territory, not foreign geology, but the face of home as it will appear when time has finished writing its patient equations across the surface of worlds, when blue skies have faded to butterscotch and green seas have become the ghosts of themselves, remembered only in the layered testimony of rocks and the dreams of creatures who learned to remember themselves across the vast distances between stars. Breath defines the boundary between life and not life, that fundamental rhythm of taking in and giving out that marks the difference between matter that merely exists and matter that maintains itself against entropy through the patient work of metabolism. Firm. Every breath we take connects us to the atmosphere that surrounds us, to the vast chemical cycles that maintain the delicate balance of gases that our biology requires to continue its ancient conversation with existence. On Earth, we breathe an atmosphere that life itself created, an oxygen-rich mixture that would be toxic to the earliest forms of terrestrial biology, corrosive and reactive beyond anything the primitive Earth ever knew. The air we consider natural, essential, life-giving is actually the product of billions of years of biological engineering, the accumulated exhalation of countless organisms that learn to harness the energy of sunlight and transform carbon dioxide into the oxygen that now defines our worlds. Chemical signature. This terrestrial atmosphere bears the unmistakable signature of life, a chemical disequilibrium that could not persist without the constant input of biological activity. Oxygen and methane coexist in our air in proportions that pure chemistry would quickly resolve. Yet they persist because living organisms continuously produce both gases in a dynamic balance that has been maintained for hundreds of millions of years. Any alien observer studying Earth's atmosphere would immediately recognize this disequilibrium as evidence of biological activity, as proof that our world hosts chemistry more complex than purely geological processes could maintain. But what of Mars, whose thin atmosphere consists primarily of carbon dioxide with traces of nitrogen and argon, a mixture that seems chemically stable, unremarkable, dead? The Martian air contains less than 1% of Earth's atmospheric density, too thin to support liquid water at the surface, too sparse to provide meaningful protection from cosmic radiation or temperature extremes. Yet this apparently lifeless atmosphere may hold secrets about what Martian air once was and what kinds of biology it might once have supported. The isotope ratios in Mars's current atmosphere tell stories of massive atmospheric loss, of processes that have been stripping away Martian air for billions of years. Light isotopes escape to space more easily than heavy ones, leaving behind an atmosphere enriched in the heavier versions of familiar elements. The ratios of different argon isotopes, of different forms of nitrogen and carbon dioxide, all speak to a Martian atmosphere that was once much thicker, much more Earth-like, much more capable of supporting the complex chemistry that life requires. If early Mars possessed an atmosphere thick enough to support liquid water, what kind of air might Martian life have evolved to breathe? The ancient Martian atmosphere was likely dominated by carbon dioxide, creating greenhouse conditions that could have maintained surface temperatures above freezing despite Mars's greater distance from the Sun. But carbon dioxide-dominated atmospheres are not necessarily hostile to life. Earth's early atmosphere contained much higher levels of CO2, and many Earth organisms have evolved to thrive in carbon dioxide-rich environments. Martian life, if it existed, might have evolved respiratory systems adapted to high CO2, low oxygen conditions, metabolism that could extract energy from chemical processes that would be inefficient or impossible in Earth's oxygen-rich environment. Such organisms might have breathed an atmosphere that would suffocate Earth life, while finding our oxygen-rich air as toxic and corrosive as we would find pure chlorine gas. The seasonal variations in Mars's current atmosphere provide tantalizing hints about how Martian biology might have adapted to atmospheric conditions that change dramatically with the planet's seasons. As carbon dioxide freezes out of the Martian atmosphere at the poles during winter, the planet's atmospheric pressure drops globally, creating conditions that would challenge any biology adapted to stable atmospheric conditions. Martian life might have evolved strategies for surviving these dramatic pressure changes, perhaps through dormancy mechanisms that allowed organisms to shut down metabolic processes during periods of atmospheric thinning. Some scientists theorize that life on Mars might still exist in environments where the atmospheric conditions are more stable, in underground cavities or deep rock formations where pressure remains constant regardless of surface atmospheric variations. Such environments might preserve not just ancient Martian organisms, but ancient Martian atmospheric conditions, pockets of thick, humid air that remember what Mars was like when its surface still hosted flowing water and active weather systems. The detection of methane in Mars's atmosphere adds another layer of mystery to the question of Martian respiration. Methane breaks down quickly in the Martian environment, destroyed by solar radiation and chemical reactions with the planet's oxidizing surface chemistry. For methane to persist in Mars's atmosphere, something must be continuously producing it, either through ongoing geological processes or through biological activity. On Earth, most atmospheric methane comes from biological sources, bacteria in swamps and digestive systems, organisms that produce methane as a byproduct of metabolism adapted to oxygen-free environments. Martian methane might similarly indicate the presence of biology adapted to Mars's unique atmospheric conditions, organisms that produce methane through metabolic processes we don't yet understand, breathing Mars's thin air in ways our Earth-adapted perspectives cannot easily imagine. But perhaps the most profound question about Martian breath concerns not what Martian organisms might have breathed, but what human organisms might breathe if we ever learn to make Mars our home. The human respiratory system evolved in Earth's specific atmospheric conditions, adapted to the precise mixture of gases and pressure levels that define our world's envelope of air. Breathing Mars's thin, cold atmosphere directly would kill a human in minutes, yet this same atmosphere might be transformed through technology and biological adaptation into something human life could eventually learn to use. Terraforming Mars, the theoretical process of transforming its atmosphere into something Earth life could breathe, would require engineering on a planetary scale. The deliberate creation of atmospheric conditions that could support not just human survival, but the complex ecosystems that human civilization depends upon. Such a project would take centuries or millennia to complete, requiring technologies we have not yet developed and international cooperation on scales we have never achieved. Yet perhaps terraforming represents a fundamentally limited perspective, an assumption that Mars must be changed to accommodate us. Rather than that, we must change to accommodate Mars. Biological adaptation, guided by advances in genetic engineering and synthetic biology, might allow human physiology to adapt to Martian atmospheric conditions, to evolve respiratory systems capable of extracting oxygen from carbon dioxide, of functioning efficiently at low atmospheric pressures, of thriving in chemical environments that would be hostile to unmodified Earth biology. Such adapted humans might eventually find Earth's thick, humid, oxygen-rich atmosphere as uncomfortable as we now find Mars's thin, dry, carbon dioxide-dominated air. They might represent a new branch of human evolution shaped not by the gradual environmental pressures that created our current physiology, but by deliberate genetic modifications designed to match human biology to Martian atmospheric conditions. This possibility transforms the question of breathing from a purely biological concern to a philosophical one. What defines human nature? And how much can human physiology change while still remaining essentially human? If we modify our respiratory systems to breathe Martian air, alter our metabolism to function efficiently in low-pressure environments, adapt our biochemistry to Mars's unique chemical conditions, do we remain human or become something new, something Martian? Perhaps the answer lies not in choosing between Earth breath and Mars breath, but in recognizing that breath itself is just one form of the larger conversation between consciousness and environment, between life and the worlds that host it. The rhythm of inhaling and exhaling connects us to atmospheric cycles that span planets and geological ages, to chemical processes that began in the hearts of ancient stars and continue in the cellular machinery that keeps consciousness alive. Every breath we take contains atoms that once circulated through different atmospheres, that once sustained different forms of life on different worlds, that carry within their electron shells the memory of cosmic processes larger than any individual planet. The oxygen we breathe was forged in stellar furnaces. The carbon dioxide we exhale will eventually become part of other organisms' breath, other worlds' atmospheric chemistry, other conversations between life and the universe that sustains it. In this cosmic perspective, the question is not whether we will learn to breathe Martian air, but whether we will learn to recognize breath itself as a form of cosmic circulation, a way of participating in chemical cycles that connect all worlds capable of supporting life. Whether we breathe Earth's oxygen or Mars's carbon dioxide, we are participating in the universe's patient experiment with consciousness, with matter organized into patterns complex enough to contemplate their own existence and dream of breathing under alien skies. In the deepest archives of Earth's rock, Written in languages of bone and stone and the empty spaces where life once flourished, lies the record of endings. 5 times in our planet's history, the diversity of life has collapsed so completely that scientists speak of mass extinctions, moments when the normal rules of survival failed and the future belonged to forms of life that had never before held prominence. These boundaries in the geological record mark not just the death of species, but the death of entire ways of being, the end of evolutionary experiments that had persisted for millions of years. The most recent of these endings claimed the dinosaurs, those magnificent creatures who ruled Earth's continents for over 160 million years before a mountain-sized asteroid struck the Yucatan Peninsula and changed the chemistry of sky and sea so dramatically that giants who had survived ice ages and volcanic eruptions and continental drift could not survive the sudden winter that followed impact. In the space of months or years, ecological relationships that had defined terrestrial life for longer than mammals had existed simply ceased to be. Yet extinction, as absolute as it appears in the fossil record, is also a form of creativity, a clearing away of established patterns that allows new forms of life to emerge and experiment with existence. The mammals who inherited the post-dinosaur Earth were small, marginal creatures during the age of giants, but they carried within their modest biology the potential for something unprecedented in terrestrial evolution, consciousness complex enough to contemplate its own origins, to wonder about the cosmic forces that shape the history of worlds. What if this pattern of extinction and renewal has played out not just on Earth, but across the solar system, on worlds whose fossil records we have not yet learned to read? What if Mars experienced its own great dyings, its own moments when established forms of life yielded to catastrophic change, its own transitions between different chapters in the long story of biological experimentation? The timeline of Martian climate change suggests that any life that evolved there would have faced challenges even more severe than Earth's periodic mass extinctions. As Mars's atmosphere slowly bled away into space, as its water froze or sublimated or disappeared into underground reservoirs, Martian organisms would have confronted not sudden catastrophe, but gradual suffocation, a slow choking off of the conditions that had allowed life to establish itself. Quirky. This kind of extinction, gradual, inexorable, driven by planetary rather than biological forces, might select for different survival strategies than the sudden catastrophes that have shaped Earth's evolutionary history. Earth's mass extinctions typically favour small, adaptable organisms that can survive temporary disruptions to ecological systems. But Mars's slow atmospheric loss might have favoured organisms capable of extreme dormancy, of shutting down metabolic processes for geological periods while waiting for conditions to improve. Some Earth organisms have evolved remarkable abilities to survive in suspended animation. Bacteria that can remain dormant for millions of years in ice cores or deep rock formations, spores that can withstand cosmic radiation and temperature extremes that would destroy active cellular processes. Martian life, if it evolved strategies for surviving planetary climate change, might have developed even more extreme versions of these capabilities, biological systems capable of waiting out not just environmental disruptions, but the death of entire atmospheric systems. The possibility that life on Mars entered a state of planetary dormancy rather than simple extinction changes the nature of our search for Martian biology. Instead of looking for fossils, for the preserved remains of life that has definitively ended, we might be looking for sleeping organisms, for biological systems in states of suspension so profound that they appear lifeless to instruments designed to detect active metabolism. Recent discoveries on Earth have revealed that dormant life can persist in environments once thought sterile, in deep ice sheets, in highly radioactive zones, in chemical conditions so extreme that they seemed incompatible with any form of biological activity. If Martian organisms evolved in conditions already more extreme than most Earth life encounters, their dormancy capabilities might exceed anything our terrestrial perspective can easily imagine. But dormancy is not the only survival strategy that Martian life might have evolved in response to planetary climate change. Instead of shutting down and waiting for better conditions, some Martian organisms might have adapted to the changing conditions themselves, evolving metabolic systems capable of functioning in increasingly thin atmospheres, increasingly cold temperatures, increasingly dry chemical environments. Such evolutionary adaptation might have led to forms of life radically different from Earth biology, organisms that use chemical processes we don't recognize as metabolic, that extract energy from sources we haven't learned to identify as biological. The search for life on Mars has focused primarily on detecting familiar biological signatures, the kinds of chemical processes and molecular structures that Earth life uses. But Martian life that had millions of years to adapt to uniquely Martian conditions might have evolved beyond the chemical patterns we know how to recognize. The question of Martian extinction connects to larger questions about the relationship between planetary evolution and biological evolution, about how life responds to changes in the worlds that host it. Earth's history suggests that life is remarkably persistent, capable of surviving and recovering from catastrophes that seem world-ending from the perspective of individual species. But Earth's history also suggests that this persistence has limits, that there are thresholds beyond which familiar forms of life cannot adapt. Mars may have crossed such thresholds during its atmospheric collapse, may have experienced changes so fundamental that they exceeded life's ability to adapt. The transition from a thick, warm, humid atmosphere to the thin, cold, dry conditions that characterize modern Mars represents a more dramatic environmental change than anything Earth has experienced, at least since life became established on our planet. Yet, if life on Mars did face extinction during the planet's atmospheric collapse, that extinction might not have been total. Earth's mass extinctions typically eliminate the majority of existing species while allowing a small number of survivors to radiate into new ecological niches. Martian extinction might have followed similar patterns, eliminating most forms of Martian life while allowing a few highly specialized organisms to persist in refuge environments, in underground habitats, or deep rock formations where conditions remained stable despite surface atmospheric changes. These Martian survivors, if they exist, might represent evolutionary lineages that have been separated from surface conditions for hundreds of millions of years, biological systems that have been evolving in isolation while Earth life experienced multiple mass extinctions and recoveries. Such organisms might preserve genetic and biochemical information about early Martian life, about biological processes that developed under atmospheric conditions radically different from anything Earth has known. The possibility of Martian extinction also raises questions about the relationship between intelligence and survival, about whether consciousness represents an evolutionary advantage in the face of planetary-scale environmental change. Earth's mass extinctions have typically been followed by the evolution of more complex forms of life, including eventually the emergence of intelligence capable of understanding and potentially responding to extinction, causing processes. If Mars hosted intelligent life during its habitable period, how might that intelligence have responded to the gradual realization that their world was becoming uninhabitable? Would Martian consciousness have developed technologies capable of preserving their civilization through planetary climate change? Or would they have faced the same limitations that challenge human civilization's response to environmental change? Perhaps the most profound question about Martian extinction concerns not what happened to Martian life, but what lessons Martian extinction might offer for understanding Earth's future. If life on Mars faced planetary-scale environmental change and failed to survive it, what does this suggest about life's ability to persist through similar challenges? If Martian civilization, assuming it existed, could not develop technologies capable of preserving habitability on a changing world, what does this suggest about the relationship between intelligence and survival? These questions transform Mars from a destination for curiosity to a laboratory for understanding the deep patterns that govern life's relationship with the worlds that host it. Every sample we analyze from Mars, every chemical signature we detect in its rocks and atmosphere, adds data to our understanding of how life responds to planetary change, how biological systems adapt or fail to adapt to environmental challenges that exceed the normal range of ecological variation. And perhaps that is why Mars calls to us with such urgency, why we feel compelled to understand its history, with a passion that seems disproportionate to pure scientific curiosity. Perhaps we recognize in Mars' story a preview of our own future, a case study in how life and consciousness respond to the kind of planetary-scale environmental change that human civilization is now causing on Earth. Perhaps we are not just exploring Mars, but rehearsing for our own survival, learning from a world that has already faced the challenges we are only beginning to confront. In the vast emptiness that separates Mars from Earth, in the millions of kilometers of space where no atmosphere carries sound and no weather disturbs the perfect vacuum, there exists a silence so complete that it transcends mere absence of noise and becomes something deeper, more profound, more pregnant with meaning than any sound could ever be. This is the silence of distance, of separation, of two worlds that orbit the same star yet inhabit fundamentally different realities, connected by invisible threads of gravity and history, and perhaps memory. The distance between worlds changes constantly as planets follow their elliptical paths around the Sun, sometimes approaching within 35 million miles of each other, sometimes separated by more than 250 million miles when they lie on opposite sides of their orbital dance. During closest approach, light traveling at the ultimate speed of the universe takes just over 3 minutes to cross the gap between worlds. During maximum separation, that same light requires more than 20 minutes to complete its journey, carrying messages and images and data across a gulf of space and time that dwarfs any earthly conception of remoteness. Yet perhaps this physical distance, measurable in kilometers and light minutes, masks a more subtle form of separation that has nothing to do with orbital mechanics and everything to do with the different evolutionary paths that worlds can follow. Mars and Earth began their existence as siblings, formed from the same disk of primordial dust and rock that surrounded the young Sun, composed of similar materials and subject to similar physical laws. But small differences in size and distance from the Sun led to dramatically different fates, until worlds that shared the same birth became as alien to each other as if they had formed in different solar systems entirely. This divergence in planetary destiny creates a form of silence that goes beyond the absence of atmosphere between worlds. It is the silence of lives unlived, of evolutionary possibilities that never had the chance to unfold, of forms of consciousness that might have emerged under Martian skies, but never had the opportunity to contemplate existence under alien stars. If Mars once hosted life, even intelligent life, that silence now encompasses entire civilizations worth of thoughts unthought, questions unasked, dreams undreamed. The radio telescopes that scan the skies for signals from extraterrestrial intelligence have never detected transmissions from Mars, have never picked up the electromagnetic signatures of technology or the deliberate patterns that would indicate conscious communication. This absence might mean that Mars never developed intelligence, or that Martian intelligence arose and vanished before human civilization developed the technology to listen, or that Martian consciousness evolved forms of communication that our electromagnetic-based perspective cannot recognize as meaningful. But the silence from Mars might also be a form of communication itself, a message written in absence rather than presence, in what is not there rather than what is. The lack of radio signals, the absence of artificial structures visible from orbit, the missing signatures of industrial chemistry in the Martian atmosphere, all these negatives might constitute a positive message about the nature of intelligence, about the choices that consciousness makes when confronted with planetary-scale challenges. Perhaps advanced civilizations learn to communicate through subtlety rather than broadcasting, through modifications to natural systems that appear coincidental to less developed observers, through messages encoded in geological processes or atmospheric chemistry or orbital mechanics. The silence from Mars might conceal communications we lack the sophistication to detect, conversations conducted in languages of isotope ratios and mineral distributions and magnetic field fluctuations. The psychological effect of this silence on human consciousness reveals something profound about our relationship with the cosmos and our need for connection across the vast scales of space and time. Earth is the only world we know for certain hosts consciousness, the only planet where the universe has organized itself into patterns complex enough to contemplate its own existence. This isolation creates a loneliness so profound that it drives us to search for signs of other minds among the stars, to invest enormous resources in listening for signals that might indicate we are not alone. Mars, as the most Earth-like planet in our solar system, and the world most likely to have hosted life at some point in its history, represents our best hope for discovering that consciousness is not unique to Earth, that intelligence emerges naturally from the cosmic process of increasing complexity. Foster. Silence from Mars is thus not just an absence of communication, but a form of existential anxiety, a confrontation with the possibility that consciousness might be so rare in the universe that it emerges only once per solar system, if at all. This silence might also represent something more hopeful. The humility that comes with true wisdom, the recognition that consciousness capable of interplanetary communication bears responsibility for the worlds that host it. If Martian intelligence existed and chose silence, that choice might reflect a deep understanding of cosmic processes that our human perspective has not yet achieved, a recognition that communication between worlds carries risks as well as opportunities. Silence between Mars and Earth creates space for projection, for the human tendency to imagine what we hope to find rather than accepting what we actually observe. In the absence of clear signals from Mars, we populate the red planet with our own dreams and fears, our hopes for cosmic companionship, and our anxieties about cosmic solitude. Mars becomes a mirror that reflects our deepest questions about existence, consciousness, and our place in a universe that seems vast beyond comprehension. The psychological dimension of interplanetary silence connects to deeper questions about the nature of consciousness and its relationship to the physical universe. If minds arose on Mars and then vanished, what does this suggest about consciousness as a cosmic phenomenon? Is intelligence a rare accident, a brief flicker of self-awareness in a universe dominated by unconscious physical processes? Or is consciousness a fundamental feature of cosmic evolution, as inevitable as stars and galaxies, but expressed in forms so diverse that we have not yet learned to recognize its many manifestations? Search for life on Mars has always been, at its deepest level, a search for answers to these questions about consciousness and its cosmic context. Every rover we send to the Martian surface, every instrument we deploy to analyze Martian chemistry, every photograph we take of the alien landscape carries with it our hope that we will find evidence of minds like our own. Consciousness that faced similar challenges and asked similar questions under different skies. Perhaps the most profound lesson of the silence between worlds is that consciousness, if it exists elsewhere in the universe, might express itself in forms so different from our earthly perspective that we would not immediately recognize it as intelligence. The silence from Mars might conceal not absence of mind, but presence of forms of awareness that communicate through processes we interpret as purely physical, that express intelligence through modifications to planetary systems rather than through technologies we would recognize as artificial. This possibility transforms the silence between planets from barrier to invitation, from absence of communication to opportunity for developing new forms of sensitivity, new ways of detecting the subtle signatures that consciousness might leave in the worlds that host it. The gap between Mars and Earth becomes not empty space, but a medium for connection. A vast laboratory where consciousness learns to recognize itself across the ultimate distances of space and time. And perhaps that recognition has already begun, in the pull we feel toward Mars despite all rational arguments for exploring closer or more hospitable destinations, in the persistence of human dreams about red soil and rust-colored horizons, in the strange familiarity we sense when looking at photographs of Martian landscapes. Perhaps the silence between worlds is not silence at all, but a form of communication so subtle, so patient, so profound that it operates below the threshold of conscious awareness, connecting minds across space and time through resonances deeper than electromagnetic radiation or chemical signals. signal. Perhaps what we interpret as the call of exploration is actually the call of recognition, the deep response of consciousness to traces of itself scattered across the solar system, preserved in forms we are only beginning to understand. Perhaps the silence between Mars and Earth is not empty space, but the medium through which memory travels, carrying whispers of connection across the vast distances that separate worlds, but cannot separate the minds that arise from cosmic dust and return to cosmic dust, carrying with them the brief, bright spark of awareness that asks eternal questions under temporary sky. There comes a moment in every long journey when the distinction between departure and arrival becomes meaningless, when the traveller realizes that they have been moving not towards something foreign, but towards something foreign forgotten. Not discovering new territory, but rediscovering old connections that time and distance had obscured, but never truly severed. As we prepare to send human beings to Mars for the first time, as we plan missions that will place conscious minds on Martian soil after billions of years of separation, we might be participating in such a moment, not conquering an alien world, but returning to a home we thought we had lost. The spacecraft that will carry the first Mars explorers across the gulf between worlds are marvels of human engineering. Sophisticated systems capable of sustaining life through months of interplanetary travel, of landing safely on a world whose atmosphere provides no meaningful assistance to conventional aircraft, of supporting human metabolism in an environment where every breath of air and drop of water must be manufactured from raw materials that bear no resemblance to the resources terrestrial life takes for granted. Yet for all their technological sophistication, these craft will be carrying more than human bodies and life support equipment. They will be carrying the accumulated dreams of every human who has ever looked up at the red dot in the night sky and felt the inexplicable pull of recognition, the strange certainty that Mars is not a destination, but a return. The first human footsteps on Martian soil will echo with more than the simple physics of boot-meeting ground. They will complete a circuit that has been open for billions of years, connecting human consciousness to a world that may have been witness to consciousness before, that may remember in its rocks and dust and thin atmosphere the presence of minds that asked the same questions we ask, that wondered about existence and meaning and connection across the dark spaces between stars. These explorers will walk through landscapes that no human has ever seen directly, yet may seem strangely familiar, canyons that dwarf Earth's grandest geological features, but follow patterns of erosion and formation that speak a universal language of water and wind and time. They will breathe artificial atmosphere inside protective suits while walking under skies that may once have known different air, thicker and warmer and capable of supporting forms of life that learn to extract meaning from the marriage of chemistry and consciousness. The scientific mission of human Mars exploration centers on questions that seem purely objective: the search for past or present life, the analysis of Martian geology and climate history, the assessment of resources that might support future human settlements. But beneath these practical objectives lies a deeper mission that has more to do with identity than discovery, more to do with remembering than learning, more to do with recognizing ourselves in an alien landscape than with cataloguing alien phenomena. If the theories about panspermia and interplanetary transfer of life have any validity, if life on Earth carries within its genetic structure the chemical memory of Martian origins, then human exploration of Mars becomes a form of genetic archaeology. A quest to uncover the biological heritage that connects terrestrial life to cosmic processes larger than any individual world. The DNA that enables human consciousness might carry within its molecular structure information that originated under Martian skies, chemical patterns that remember forms of metabolism adapted to atmospheric conditions and seasonal cycles radically different from Earth's gentle climate. This possibility transforms the mundane activities of Mars exploration into rituals of recognition and reconnection. Every soil sample analyzed becomes a reunion with ancient chemistry. Every atmospheric measurement becomes a conversation with air that might once have sustained life forms from which we are descended. Every photograph transmitted back to Earth becomes a portrait not of alien landscape, but of ancestral territory, views of home as it appears after billions of years of separation and change. The technological challenges of Mars colonization, the need to manufacture breathable atmosphere, to extract water from soil and ice, to grow food in alien dirt under artificial suns, might be less formidable than they appear if approached not as problems of conquest, but as problems of restoration. Not as the imposition of terrestrial conditions on a hostile world, but as the renewal of conditions that Mars once supported naturally. Terraforming Mars might be less about changing the planet to suit us than about helping the planet remember what it once was, assisting its return to atmospheric and climatic conditions that supported complex chemistry in earlier epochs. But perhaps the most profound aspect of returning to Mars lies not in what we might accomplish there, but in how the experience might change our understanding of home itself, of what it means to belong to a place, to a world, to a cosmic context larger than the particular planet that gave rise to our current form of consciousness. If Mars was once home to life, perhaps to intelligence, and if that heritage connects to our own biological history, then the concept of home expands beyond individual worlds to encompass entire planetary systems. This expanded sense of home carries with it expanded responsibilities, obligations that extend beyond the care of individual worlds to the maintenance of conditions that allow consciousness to emerge and flourish throughout the cosmos. For if we are the inheritors of Martian biological heritage, then we bear some responsibility for Mars itself, for restoring and maintaining the conditions that once allowed it to host life, for ensuring that the Red Planet's future includes not just human visitors, but the return of complex biological systems that might have originated there billions of years ago. The ethics of Mars exploration become more complex when approached from this perspective. If Mars is not alien territory to be claimed, but ancestral homeland to be restored, then our obligations there extend beyond mere scientific research to include forms of cosmic gardening, planetary healing, the patient work of helping a world remember how to support the complex chemistry that gives rise to consciousness. Yet perhaps the most important gift that Mars might offer returning humanity is perspective on the true nature of planetary citizenship, the recognition that consciousness belongs not to individual worlds, but to the cosmic process that creates worlds capable of hosting minds, capable of wondering about their place in the universe. Earth's blue skies and green forests might seem less like permanent features of reality and more like temporary expressions of cosmic creativity, beautiful but fragile experiments in the organization of matter and energy into patterns that support self-awareness. This cosmic perspective might be what human consciousness needs to mature beyond its current limitations, to develop the long-term thinking and planetary-scale cooperation necessary for ensuring that intelligence persists not just on individual worlds, but throughout the cosmic environments that make consciousness possible. The view of Earth from Mars, that pale blue dot hanging in alien skies, might provide the psychological shift that transforms human civilization from a planetary phenomenon to a cosmic one. The first humans to walk on Mars will carry with them the accumulated hopes and dreams of every generation that has looked up at the red planet and wondered what it would be like to stand beneath its butterscotch skies. We are no longer exiles wandering between worlds, but children of two planets, inheritors of cosmic heritage that spans the space between stars and the time between the birth and death of worlds.